probably have seen before in physics in 12th grade. Okay, so brief overview of concepts before we get started with problems. So we want to define work done by a force the work done is represented by U, and du is actually the work done by force acting and causing a motion dr. So if you want to find the total work done, you got to integrate this equation from wherever position 1 to position 2 equals integral f dot dr from r1 to r2. Now this one assumes that you know the force as a function of uh, distance, right? If you know f as a function of r, then you can integrate the equation. Another thing to note is that this is a dot product. What does the dot product do? It gives you a scalar, right? If you have a dot b, so if a dot b, and this is I plus j, and you dot it with 2i minus j, then what you need to do in order to find the dot product is take the I component, multiply with the I component of the second vector, then you'll have plus the j component, the magnitude of the j component times the magnitude of the j component of the other vector. So it'll be 2 minus 1, which will be 1. Okay, it's a scalar. Very common mistake. F dot r, people take the cross product, which is wrong. You will get a scalar for f dot r. It's not a vector. Well, let me write this as u12. Okay, this is the work done in moving an object from 1 to 2. The other way in which you can interpret f dot dr is from the definition of the dot product. F dot dr is the magnitude of f, magnitude of dr, and the cosine of the angle between f and r, right? This is f, this is dr, then the cosine of the angle between the two gives you the magnitude. So there are two ways to find the dot product. One is you take the vectors and take the dot product, or you can use this formula. If you know the angle between the two vectors, then just the magnitudes times the cosine of the angle gives you the force, the work done. Okay, simple 1D case. It's also important to figure out the sign, because if you don't get the sign right, you'll get the problem wrong. So if the force, so this is a block subjected to force F, leads to a motion to the right, then u12 is F times R2 minus R1, and it is positive, right? Because the force acts in the direction in which the particle or the block moves. If, however, the force is applied to the right, but the motion is to the left, and this happens, for example, in the gravity, right? Sometimes the block has a velocity upwards, so even though the mg is acting downwards, the motion is upwards. So in this case, the same magnitude is true, but the sign is negative magnitude, because the work done is negative. Another thing to note is when there's a normal force, the work done by the normal force is 0, right? Because if you take n dot dr, then you have magnitude of n, magnitude of dr, times cosine of the angle between n and r. So n is, the angle between the two is 90 degrees, so it's going to be 0. So forces which are normal to the displacement will have a work done equal to 0. Okay, a few more things and we'll be done. Uh, so this chapter is filled with problems on springs and motion under gravity, and so it's important to figure out the expression for work done when there is gravity and spring forces. So work done by gravity. So work done by gravity is, now what we do is we assume y is upwards, right? That's a convention. Mg acts downwards. So the way you compute this is force, which is mgj, right? It's negative because the force is downwards. Our convention is upwards is positive, so that's going to be the magnitude of the displacement. So when you take the dot product, you need to take this times this, right? So it's negative mg dy from y1 to y2, which is minus m So this is the formula for the work done due to gravity. Okay, it only holds true based for this convention, which is upwards is positive. The next thing we want to understand is work done by a spring force. Okay, what does a spring do? Well, if you stretch a spring, so this is the normal unstretched. If you pull the spring, so you stretch it like so, then the force is always going to be in which direction? So what's the force when you stretch the spring? Is it to the right or to the left? It's opposite to the motion. So a spring wants to go back to its original length. The force which gets it back to the original length is going to act to the left. So F is this way. So the work done, assuming that this is the right side is the positive x direction, we would have Fs minus Fs I because they are x to the left times ds times I. That's because right side is positive. So when you take the dot product and you want to integrate from S1 to S2, I'm just going to substitute the value for Fs. Fs is minus k times S I dot ds I. So it's minus k S2 S1 S ds I dot I is 1. So we would have minus half k S2 square minus S1 square. So the work done is minus half k S2 square minus S1 square. Okay, the final thing before we start solving problems is something called principle of work energy, and this will be used to solve problems. So principle of work energy. It states that the work done Okay, this is something which you compute for spring, gravity. I've given you the expression is always equal to the change in kinetic energy, which is half mv2 square minus half mv1 square. And that's always true. Okay, any questions on this? Okay, so where does this fit in? Why do we actually need to know principle of work energy? So given a problem, it turns out that principle of work energy is actually a shortcut of solving many of the problems. Okay, you could use F equals ma to solve the problems, or you could use principle of work energy. So given a problem, and once you've identified it's a problem on kinetics, that is forces, uh, draw free body diagram. Okay, then you're going to use either one or two or three. So two is, this is what we did in chapter 13, 17, which is equations of motion. Okay, uh, so you could do the problem using equations of motion. That will always work. However, this number 3 is chapter 14, and the next chapter, which you're going to do, 18, is actually a shortcut of solving problems by using principle of work energy. Okay, I would recommend using principle of work energy when you ask to solve for velocity as a function of distance. Okay, you can also do, as I said, you can also do this problem using this method. Number 2 will always work. F equals ma will always work. However, this turns out to be a shortcut to do problem. So if you see a problem which says find velocity as a function of distance, you're better off doing principle of work energy. Okay, and then the final step is you need to integrate in case you're asked to solve for kinematics, other things like positions. Okay, I discussed about this, but we'll see where to apply this when we have this case. So we'll see how this is useful when we do the problems today. Here's the first problem. So design considerations for the bumper B. Okay, on the 5 times 10 raised to 6 gram, which is 5 times 10 raised to 3 kilograms train, requires the use of a non-linear spring having load deflection characteristics shown in the graph. Okay, so this is the force displacement curve. Note that it is non-linear. It is not, usually it's F equals kx, it's ks square. Select the proper value of k, so this is the unknown, so that the maximum deflection of the spring is limited to 0.2 meters when the car traveling at 4 meters per second strikes the rigid stop. Neglect the mass of the car wheels. So what it's saying is that if you see, this is barely visible here, there's a spring here, and this train is moving at 4 meters per second. Okay, this is the stop. So it's moving at 4 meters per second with a rigid stop. So what's happening is this spring comes into contact with the rigid surface, and the maximum compression you allowed is 0.2 meters. So it should stop when the deflection of the spring is 0.2 meters. So where is that energy dissipated? It's dissipated in the spring. It's stored in the spring. So you find the spring constant, so that the deflection of the spring is 0.2 meters and the train comes to a stop. So what you notice in this problem is you're given the speed 4 meters per second, you're given the displacement 0.2 meters, so velocity is related to displacement. So here is a place where I would recommend using principle of work energy. You could also do this using F equals ma, that is, you could draw a free body diagram when it comes in contact, find the force. You will get an expression for acceleration, integrate that expression, and get the value for displacement as a function of distance. Sorry, velocity as a function of distance. So, but that is more time consuming. So we're going to use principle of work energy. Before that, let me draw the free body diagram. And train contacts the stop. So there would be a friction. The spring force will be to the left because it's decelerating the train. Mg will be upwards and the normal mg will be downwards and normal force is upwards. So then we'll use principle of work energy. The reason is because v is given as a function of distance. Okay, so what does principle of work energy say? It says that the net work done is the change in kinetic energy. Okay, the net work done is the work done to the spring. So the spring is applying a force to the left. So it's minus Fs is a spring force. ds is to the right, so it's positive, and we got to integrate the displacement from 0, initially it's 0 to 0.2. So what is Fs? Fs is coming from this curve. It's a non-linear spring, so I need to put that expression for the spring force. So it's 0 to 0.2 minus k s square ds. So it's minus k divided by 3 s cubed. Well, let me write it this way. Minus k is out, s cubed divided by 3, 0.2 and 0. So that is 0.2 cubed divided by 3. I'm going to keep it as it is. Okay, the initial kinetic energy. What's the initial kinetic energy of the system? It's half mv1 squared. The mass is, what's the mass? It's 5,000 kilograms. So 5,000 times the velocity is 4 square. What is the final kinetic energy? It's 0, right? Because the train is supposed to come to a stop. So plugging all this back in that expression, we have minus k times 0.02 cube divided by 3 equals T2, which is 0, minus T1, which is half times 5,000 times 4 square. Okay, so you can clearly solve for k because that's the only unknown in that equation. So solving for k gives me 15 times 10 raised to 6. Okay, what's the units on the spring force? Normally the units are Newton per meter, right? Because the force is newtons and spring force is, well, it's k times x. So in this case, it's not Newton per meter, it's Newton per meter square. And that's true because as F equals kx square, right? Units are going to be Newton divided by meter square because that's the relation between F and x for a nonlinear spring. For this particular case, you could have any expression you want. Okay, next question. The 8 kilogram block B is moving with an initial speed of 5 meters per second. If the coefficient of kinetic friction between the block and plane is 0.25, so this plane is non-frictionless. It has a coefficient of 0.25. Determine the compression in the spring when the block momentarily stops. Okay, so what's going on is it's moving at 5 meters per second. This block really is slowing down and it's moving because of friction. And at some point of time, it arrives here with a non-zero speed. Okay, it could potentially be that it could stop here, but in this case, it actually has a non-zero speed here, because of which it compresses the spring. You're going to find the maximum compression of the spring when the block comes to momentarily rest there. So all along, it's going to be acted upon by the friction. It's going to be slowed down. Okay, so first of all, there are springs involved, there are forces involved, so it's a kinetics problem. Okay, so let's draw the free body diagram. Before B touches the spring, so before it makes contact with the spring, we would have normal force mg, and then there is a friction force which is decelerating the block. We can also draw a free body diagram after B touches the spring. So in this case, would be the normal force, there would be mg, friction will still be there because this whole surface has friction, so friction force is Ff. In addition, there will be a spring force, let's call it Fs. Okay, now we have one of the two options. We could use F equals ma, or we could use principle of work energy. The reason why we could use principle of work energy is because, again, in this problem, you are told to find displacement at a given initial speed. So velocity as a function of displacement is given, or rather, you're told to find that. So makes sense to use principle of work energy. If you were to use what you learned in chapter 13, which is F equals ma, this is how you'll proceed. You'll first find the velocity when it arrives here using what? That free body diagram, use F equals ma, solve for the acceleration, integrate, get the velocity here. After you get over there, use this free body diagram, write F equals ma, right? And then solve for acceleration, integrate it, and then find the displacement when velocity goes to 0. So you'll have to break it down into 2 steps. You have to use F equals ma there, integrate to get velocity, use F equals ma here, integrate to get velocity, and that will give you the answer. So it's 2 steps. However, using principle of work energy, you can do it in a single step. So that's the advantage of using work energy. So I'm going to solve it using work energy, but please try to do it using F equals ma. That's a totally legitimate way to do this. So principle of work energy. So again, as V equals F of S is to be determined. So U12 is equal to T2 minus T1. Okay, so actually we have, well, okay, so let's find the work done from 1 to 2. So 1 is initial and 2 is when lock comes to rest. So what are the external forces acting on the block? There is friction force and there's a spring force. as you can see from the free body diagram, the friction force acts before B touches the spring and after B touches the spring. So the work done by the friction force is Ff times the total distance covered, right, from here all the way to this. Let's call this distance as x, this distance as okay, so this distance is 2, and then let's say that it's compressed by a distance of x. So that force of friction is going to act the complete distance, so work done is for the complete distance. So this is going to be 2 plus x. Okay, how is the force acting? The force is acting to the left, friction force. What's the displacement? To the right. So since F is opposite to the direction of x, we have a negative for the work done. The spring is also acting to stop the block, right? So the spring, the work done due to spring was derived earlier. So it's negative half k s2 minus s1 square. I'm going to use the same formula here. Minus half k, in this case s2 is x, and the initial displacement is 0, so it's 0 square. We know that ff is mu k times n, but n is mg, so mu k mg. T1 is the initial velocity, so it's half mv square, half times mass times velocity square, which is half times 8 times 5 square. The final velocity when it comes to rest is 0. So we can say that from 1 minus mu, just put the values here, 0.25 times 8 times 9.81, so 0.25 times 8 times 9.81 times 2 plus x minus half times k. K is 200 times x square equals half mv square. So the final velocity is 0 minus half times 8 times 5 square. So when I write this equation, you see that the only unknown is x. It appears here, it appears here. So you will get a quadratic equation. A quadratic equation has two solutions. In this case, when you solve this, you'll see that one root is negative and one root is positive. The negative root, it should be discarded because it gives a nonsensical value. X has to be positive. So solve the quadratic equation, ignore the negative root, and solve for x. So x comes out to be 6875 meters.